right, so let me start with saying that my dogs are in this room, so we'll see how this goes. So this is the last, almost the last section, 1.3. In studying nature, scientists make observations and form a test hypothesis. This is an important section because this is what we're going to be doing a lot in lab. So we're going to use inquiry meaning like we're asking questions, making observations about the world around us. So the word science again is a lot. If you know Latin, that's actually probably a benefit because a lot of these terms are Latin and it means to know. It's a way of knowing. Now we have two different ways of looking at a situation. We have what's called inductive reasoning or deductive reasoning. For inductive reasoning, we draw conclusions from many observations. Deductive reasoning is a way to come up with, you come up ways to test a hypothesis, a proposed explanation for a set of observations. I am big on pictures. I think pictures give us a better idea of what we're saying. So I have this picture in here. So when we talk about deductive reasoning, okay, so we have a theory already, like for instance, the cell theory. And then we make some kind of hypothesis after, and generally we make that hypothesis after the observation. But then we're literally going to test as to whether our observation supports or rejects that theory. Right? And we'll talk about the word theory and how it is different than what people just say in casual conversation. The other approach is the opposite direction where we make an observation, we see patterns, we test hypotheses, and from that we come up with a new theory. Okay. So inductive is knowing, well, I know this theory, so my observation should follow that theory. Therefore, I'm going to test and make sure it does follow the theory. But the other one is and these are usually tons of observations, we see these patterns, and then we go ahead and start testing our hypothesis. And, we have to have several, like hundreds of experiments that basically come to the same conclusion in order to design or come up with this theory of explanation. So right here is, how is theory differ from a hypothesis? So scientific theory is it's much broader in scope than a hypothesis. And usually, um, it generates new specific hypotheses which can be tested, and it's again supported by a large and usually growing body of evidence. So here for a hypothesis is an educated guess. It's not tested yet, nor or just not tested much. Versus a theory, which is a well accepted answer, well tested, supported by many experiments. So a lot of us, when we see a problem, we'll like make a suggestion for a solution, and then we might say, "Oh, well, it's just a theory that might work." No, 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 no. It would be proper to say it's just a hypothesis. Okay, so a big difference between hypothesis and theory. So what we use is a hypothesis. Again, our hypothesis is a possible explanation for an observation that we made. And in this case, we're going to go old school, an old school flashlight. Now we're going to use deductive reasoning. All right, remember our deductive reason. This, if I can go back real quick. Deductive, which means we have a theory, we know, we understand that principle, we make an observation, the flashlight does not work. We're going to come up with our hypothesis and we're going to test it. All right. So in this case, we're going to test, the possible explanations or hypotheses as to why your flashlight does not work. All right. Now, a hypothesis has to have two components. It has to be testable. It has to be something you can test. Set up an experiment and test it. And falsifiable, meaning that it is able to potentially be proven wrong. So here's our observation. We ask questions. We come up with there's two possible answers or two possible hypotheses. The batteries can be dead or the light bulb can be burnt out. So our predictions here, replacing batteries will fix the problem. The other one, replace the bulb, will fix the problem. We're going to experiment. We're going to replace the batteries. All right. Now this is key. I want you to understand this. Okay. So the test falsifies or the hypothesis. So it wasn't the batteries. Notice the light bulb now working. Okay, so that hypothesis does not work. So now we're going to go to hypothesis two. Then we'll replace the bulb. The flashlight works. Okay. Very, very important. We are not testing both. You can have multiple hypotheses, but you only test one at a time. It's like your car. If your car didn't run and your mechanic put a bunch of different parts in it, and then it worked and you're paying for three or four different parts and you ask what was wrong with it and your mechanic said, well, I replaced this and this, and you're like, okay, well, which one was broken? And I don't know, I just put four parts in. You're paying for four parts. I don't know exactly what was wrong. You would be a little upset. All right, so even the mechanic will be like, my best guess is I think it's this. Test it. If it's not, move on. If it works, we've got the problem solved. All right. Use scientific method all the time, every day in your regular lives. So again, we're going to make an observation. We're going to ask questions. We're going to formulate a hypothesis. We're going to predict what will happen if our hypothesis is correct. And then we'll set up an experiment to test it. If it does not support the hypothesis, you can use the Mythbusters stuff, it's busted. Is it supported? Is it plausible? Is it busted? So if it's busted, we have to come up with another hypothesis. If it worked, it's supported, we're good. So this is called the scientific method. So the first thing we're going to do for step one and two is, again, make that observation and ask a question. So I'm just going to use this example of Miracle-Gro. Okay. Does Miracle-Gro really work? Or am I wasting my money on fertilizer for nothing? So next I'm going to come up with a hypothesis. If you have a hard time, you can either use if then for the hypothesis or the prediction. It really does depend on what the teacher wants, the instructor. I don't care. Okay. So if you form your hypothesis and say, if I use a fertilizer, in this case, it would be more, I'm not just asking any type of fertilizer. I'm asking if I use Miracle-Gro, then the plants will grow better. And of course, if I was to, I'm trying to go back one step. If I was to make a prediction and said, well, um, if I, so when using Miracle-Gro, I expect my plants to grow bigger. The hypothesis and your predictions that sound almost identical. Just kind of reword the sentence. So now I'm going to set up my experiment. Now notice in my experiment, I've got three plants in each group. I have group A and group B. Okay. And I have three in each sample size. And I'll explain what's so important about group A and B. All right. So we've got our two groups. Okay. Oh, I think, okay. So you need to have, there are different things. There's called controls where you keep everything the same. And then we have what's called a control group. Okay. So a control group is the group that's not getting the, um, I'm trying not to use too much complicated language here. It's the group that's not getting the treatment. Okay. I'm trying not to use the independent variable. Okay. The experimental group is receiving the question that you're asking. Okay. What you're testing, the independent variable. If I was to give all the plants the Miracle-Gro, I wouldn't know if it worked or not. I have no comparison group. So your control is really your comparison group. It's what you're comparing to say yes, it worked or no, it didn't. Look, group A did not grow as much as group B. Maybe, if all of them grew the same height, you wouldn't know. Okay, you wouldn't know if the fertilizer, maybe this was your control group. Then you can say, oh no, the fertilizer did worse. Okay, so we do need a comparison group. So that is our control group. Okay, so again, used to compare against. So we have our control and our experimental. Now variables. Maybe your teachers use controls here. We're trying not to use that because we don't want it confused with your control group. So we're using this term standardized variables. Variable meaning that is what you change, but in this case, and standardized means it's the same. So what we're saying is that, well, these are things that could be different, but we're choosing to keep them the same. So for example, in my previous setup, the pots were the same size. I put the same amount of soil, the same type of soil. I watered them with the same amount of water because if I put more water in one group, I wouldn't know if it was the Miracle-Gro or that they got more water. I want to make sure that they're both getting the same amount of sunlight. So all of these things, everything else in your experiment needs to be the same. There's only one thing you're going to change, and that is what that thing you're testing called the independent variable. Okay, right here. So in this case, our independent variable is the fertilizer. The dependent variable is how um your samples, your whatever item, whether it's a test tube you're messing with or a live specimen, okay, it's the result of the change in that particular experiment. We're looking for what change we're observing to see that is, depends on that independent variable. And in this case, our independent variable would be the plant growth. Does the plant growth depend on the fertilizer? We're looking at depends on the independent fertilizer. Step 5 and 6. The data and analysis. So if the experiment is quantifiable, scientists love quantifiable experiments. Quantifiable means you've got numbers, you can collect data, you can look for trends. You cannot argue with numerical data, quantifiable data. Okay. Just like in math class, you haven't answered that problem. It's either right or wrong. Versus like art. If your art, maybe your art teacher doesn't like it, your style of painting, and they give you a lower grade. Okay, that would be something that would be um, what we call qualifiable. So quantifiable, you collect, and then we have qualifiable, and that's where you're making observations based on taste, touch, smell, hear, etc., your senses. So in this case, with the art teacher, they're using their eyes, right? They're looking at your painting, and again, they may have their own preferences and their own biases. And so, and you guys may have had this experiment where you had maybe one year your English teacher loved your essays, and then you wrote the same style and format and everything for the next year's English teacher, and they didn't really like it. Okay, so that is qualifiable. But like I said, we love if you can quantify it, that is awesome. Oop. Okay, so let's see the next thing. I keep clicking too fast here. All right, so with that data that you collect, we don't just want some data table. I mean, we need to have a data table if our experiment is quantifiable. But we also want to look for those trends, and those trends are best seen in a graph. And so we are going to then graph our data so we can see those trends. The dependent variable is always on the x, your x-axis, the bottom one. Okay, your dependent would be on the y-axis, right? So when we look at this particular graph in our example, like the y-axis would be our height in centimeter, and then our x-axis would be, we could do it depending on how you set up your experiment. Maybe you set up your experiment with different quantities of your fertilizer. All right, so after maybe 30 days, you take that measurement of maybe full strength, half strength, double strength. No, you will need your no fertilizer for your comparison group. Or maybe you're looking at your specimens over time and you're taking um, multiple measurements. So maybe you're measuring the same plants every week, in which case then you're measuring over time. So this is where we really need to understand graphing and how to represent our data. We need to understand what kind of graph to use. Would you be using a bar graph? Would you be using a line graph? So those are things that we need to work on this semester as well. And in conclusion, generally when you get done with your lab, you're going to write it up. Conclusions should generally start with, in this lab, and kind of give a brief summary of what you did in the lab. You need to state your hypothesis. My hypothesis was how, it was supported by our experiment and then explain why it was supported, or it was not supported and explain why it was not supported. You're kind of explaining your your results. I also like to see generally in there sources of errors. Like maybe you say, oh, it wasn't supported. However, we found out that we did this. Or even if you did support it, you could say, well, you know, maybe this happened in your lab. Maybe you could, improvements would be another. It's like, our data was maybe not as precise as we would have liked it. Moving forward, we could have measured it this way. So just kind of give me your sources of error, things that may have gone wrong. Maybe you had different people measuring at different times, and they may have been measuring a little bit differently than you were. Maybe it it makes your data not quite as precise as you would like it. Right? Then you can explain, oops, this is what happened. That could have skewed our numbers a little bit better, or a little bit. I want to say better. Although sometimes we know making mistakes can give us the data that we want a little better. That does not mean throw out data you don't like. That's science. Um, so then, like I said, describe any relationships, sources of errors, and improvement. And then generally in the science community, what happens after that experiment, it's all written up. We'll ask for peer review. So they will have some of their colleagues possibly, well, definitely, usually you have your colleagues read it first, look over it, make sure everything looks good. And then if you're going to publish it, you would be sending that into that particular journal. They generally have people on staff in those different areas that they would send it to and have them critique it, look over it, and then from there, they'll decide whether to publish it or not. Of course, with the internet today, things are a little bit different, whether you put those things out there through one of the journals, kind of preliminarily put it up somewhere on the internet to talk about your lab. Um, and it's really kind of important because sharing your information, making your finds, sharing it is always really important because we don't want to waste time and money doing experiments that some other group has already done and it didn't work. You know, maybe it didn't work because they didn't do one of the pieces the way you would have done it. So it's really good. And a lot of science do that. They read papers and see what's going on and they go, you know what? I want to try this, or they tweak it, they modify it. Maybe they go in a different direction with it. So it's just really, really important for the scientific community to interact with one another as that learning community, so that we can solve problems that we're trying to solve every day. So that is it for section 1.3. Again, any questions, please feel free to reach out to me. And then I will see you in the next video.